This slide is described as error in using numerical methods for applications, as opposed to error in using numerical methods without any applications in mind. Here, I'm also thinking about applications. When you think about applications, there are 5 sources of errors in your final answers, right? I'm talking about errors in your final answers. It doesn't mean you made a math error. I mean, your final answer is just wrong for some other reason. You didn't make any math mistakes. There's model error. This arises because the mathematical model is not a perfect reflection of reality. A prime example being the example we did with free fall and air resistance. We have no idea if that model we talked about at the start of class today is going to apply directly to a certain situation with a certain ball or a certain feather. Or maybe a box, a cardboard box. You have no idea how good that model is going to be. For a given situation, for a given feather, say, you try it, see how it reflects reality. If it seems to do okay at first, then you have more confidence in it, but you want to gather more data about how good it is. A second source is measurement error. Inexact measurements, like you're timing the ball when it hits the ground, and you're just doing a bad job in your timing because maybe you're just trying to do it, eyeball it, and hit your stopwatch on your phone, and you just do a bad job in your estimations of your measurements. You're just a sloppy experimental scientist, right? If you actually have to do measurements on the job, don't be sloppy. But even if you're not sloppy, there's still going to be a little bit of measurement error. You want to minimize it. The third source of error is called the round-off error. This was related to what you saw in the reading about floating point arithmetic and that kind of stuff. In the numerical methods class with more focus on computer programming, we'd probably get into that in more depth. It arises from inexact representations of numbers in computers. Here in numerical analysis, we're not really going to focus on that. You should be aware of its existence, but it's beside the point of the main thrust of our course here. Numbers, real numbers, cannot be represented exactly in computers. Most solutions of most equations are irrational numbers. Most real solutions of most equations are irrational numbers. They're not rational. Their decimal expansion goes on forever without a repeating pattern. Yet computers have to represent things in a finite way. Computer representations of numbers are always rational, and they're not even all rational numbers. Certain subset of rational numbers is the way computers represent numbers internally, and it causes errors, especially when you're dealing with either really small numbers or really big numbers. There's rounding error. This is the most common kind of error that students will make on tests where they have to solve an applied problem, is they just round too soon. And then that error propagates. You should only round at the end. Keep as many digits of accuracy as you can along the way. Only round at the end. Fifth error is called algorithm error. It arises because of our numerical methods are, by nature, imperfect approximations. That's what we're mostly concerned with in this class. Algorithm error, or you could also call it theoretical error. Like with the bisection method, the fact that the theoretical error gets cut in half with each step because you're bisecting the interval. And there's a theorem in section 2.1 that describes exactly how that bisection error arises or behaves. We are mostly concerned with 5. If we didn't care about applications, then all we'd care about would be the last 3, 4, and 5. Okay. So it's important in real life, if you're going to become a person who does measurements and mathematical models on your job, to know about all these sources and to minimize them as much as possible. With the algorithm error, there's always a trade-off though. In trying to minimize the algorithm error, you typically need to either do more steps or a more accurate, but perhaps harder method. And so you might not understand it as well, or it might be harder to program or that kind of thing. How are we doing on time? 10 minutes. I do want you to know in the reading from section 1.2 about actual, absolute, and relative error. Suppose P star is an approximation to the real number P. So P is the unknown real number that we want to find. Find is the wrong word. We want to approximate. P star is an approximation to it. Probably P star is a rational number and P is irrational. The actual error is defined as the actual value minus approximate value. It's P minus P star. And it's very fortunate that that goes in alphabetical order, actual coming before approximate. Actually, in statistical context especially, this is typically written as observed value minus predicted value. And that's also fortunate because O comes before P. An observed value from data minus a predicted value from some model. Makes sense that the predicted would be kind of like an approximation in a sense. And the observed value would be true, the true value. It's somewhat analogous. Absolute error is just the absolute value of the actual error. Absolute value of P minus P star. Realize P minus P star could be positive or negative, right? This thing here could be positive or negative. It'll be positive when P star is smaller than P, which is a little confusing. If your approximation is too small, that corresponds to a positive error. And it's negative if P star is too big, because you're subtracting a bigger number. Negative error corresponds to an approximation that's too big. A little confusing. That might be the opposite of what you would expect, but this is the standard way to do it. And there is a good reason for that. That also comes up in statistics. What we most care about typically is the relative error. It's the absolute value error divided by the magnitude of P. Take that absolute error and divide by the absolute value of P, assuming P is non-zero. But if P were zero, that would be easy to approximate, right? It's a nice simple integer. You know, if the answer really were P equals zero, you could just tell probably. So we're assuming P itself is non-zero when we divide by this, so we don't divide by zero. And if this ratio is equal to say 0.01, you often write that as a percent, 1%. A 1% relative error. Think about that. If P is small, the relative error could be large even if P is close to P star. Because you're trying to approximate a small number. On the other hand, if P is big, say 1,000,000 something, even if the absolute value is big, that could be a small fraction. It could be a small relative error. You're trying to approximate 1,000,000 something, or say 1.2 million something with 1.3 million something, then you're, relatively speaking, not too far away, within, say, 10% or so. There's also information about significant figures in the book, but we really don't worry about significant figures. We're more concerned with these things. What happens in this class is we have theorems that come up with bounds for these things, especially the absolute error and the relative error. And we want to use those theorems like in section 2.1.